All right, so last time we covered carbon-13 NMR, and I hope you've had a chance to practice that a little bit and recognize that really carbon-13 NMR is very easy. It's a way to basically just simply count the number of carbon atoms of different types in a molecule. So we can tell, for example, if there's a ketone in the molecule, there'll be a carbon-13 NMR signal at about 200 ppm on the mystery ppm scale that we'll talk about tonight. If there's a methyl group, it will be at the other end of the spectrum. We'll see one signal for each separate, chemically distinct carbon atom. It's not quite the same as counting the total number of carbons in a molecule because, as we saw, symmetry can sometimes interfere. So, but what it does give you is a minimal number of carbons from which you can work your way towards a molecular formula. So let's just very quickly finish up here. This is mostly physics. This is mostly about how NMR works. We take a sample that contains spinning nuclei, and in the example from last week, those nuclei are carbon-13 nuclei, and they have nuclear spin. They could be forms of proton nuclei that we'll talk about in a minute. So these little nuclei spin in the absence of a magnetic field. They spin around random axes, and they create little magnetic moments that point, therefore, in random directions. But when we take that sample and pop it into a large magnetic field, which is created as part of our NMR spectrometer to measure NMR spectra, then the nuclei are either spinning clockwise or anti-clockwise, and their magnetic moments align either with or against the field. Because we're in the quantum world, there are only two spin states called alpha and beta for a spin-half nucleus, such as a proton or a carbon-13. And when the little magnets line up with the field, that's lower energy arrangement than when the magnets line up against the field. It's like the field it's like a magnetic compass needle. It's spontaneously aligned such that the north end of the compass needle points towards the north end of the Earth's magnetic field. There's a little bit of energy difference here, but not much. And the difference here is about 50.001% of nuclei in the alpha spin state pointing up. They're lower in energy. 49.999% are in the beta spin state pointing down. But that gives us enough of a difference that we can observe absorption of energy as the nuclear spin states flip. So if I take this situation here and apply radio frequency energy in the radio frequency region of the electromagnetic spectrum, I can make the alpha spin states flip to beta, provided I provide exactly the right amount of energy to the system. And this is true for both protons and carbon-13 nuclei. So we have an energy gap, and we can essentially excite the nuclei through the spin transition from alpha to beta by applying exactly the right amount of energy, exactly the right frequency to make them hop from up the energy gap. Too little energy, nothing happens, no absorption. That's the baseline of our carbon-13 NMR spectrum. Too much energy, we can't do that transition because the photon has to be completely absorbed to cause the transition. So we need exactly the right amount. And you'll notice in the carbon-13 NMR spectra that we get very sharp lines, very sharp peaks, high resolution, two carbons that are very similar but distinct, very close in chemical shift, but we can see two lines still, and we can therefore count the carbon atoms. Okay, so the stronger the magnetic field, the greater the energy gap, and that's why we work our way towards bigger and better magnets in our NMR machines. So the difference here, the reason that all carbon nuclei do not resonate at the same frequency, and the same is true of protons, of hydrogen nuclei, is that they are shielded by the electrons. So a different electron density around a nucleus means that it has different chemical shift. And so those electrons circulating around the nucleus alter the apparent magnetic field that's felt at the nucleus and alter very slightly that energy gap so that we get different absorptions corresponding to nuclei in a molecule with different electron density. So if we have a strongly electron withdrawing atom on a carbon, such as a halogen, carbon-chlorine bond, the electrons are pulled away from the carbon. The carbon is delta plus, the halogen delta minus. So there's less electron density around the carbon, and the resonance shifts to higher parts per million. So the last few slides tell us a little bit about that. When alpha and beta undergo spins flip, we say that the system is in resonance. That's where the term nuclear magnetic resonance comes from. Nuclear because we're dealing with nuclei, magnetic because we're putting them in a magnetic field, and resonance because we're making them resonate, shake between the different nuclear spin states. It's all spin, rock and roll in the NMR world. So notice that the term resonance here, it's important to distinguish this particular type of resonance. It's resonance like a bridge shaking, right? You've mostly probably seen those pictures of bridges that go into resonance and they shake and vibrate and then eventually fall down, right? It's that type of resonance that we're talking about here, different from what we mean when we apply the term resonance to talking about electrons in molecular orbitals. So NMR requires a strong magnetic field. Strengthened magnetic field affects the energy gap. Bigger the energy gap, the larger the difference between the total number of nuclei in the alpha and beta spin state, the more sensitive the NMR machine. And in fact, NMR is innately a rather insensitive technique, much less sensitive than infrared, right? Much less sensitive than mass spectrometry, where we're counting molecules arriving at a detector one by one, remember, in a mass spectrum. So in mass spec, if we get 1,000 molecules with a certain molecular weight arriving at a detector, we get a significant signal. NMR, we need much more sample, milligram quantities of sample. So to get around that problem, we keep moving to higher and higher magnetic field. Apart from that, it means that we can keep writing grant proposals for bigger and better machines, okay, which seems to be the thing to do in science, as you know. And but we really are going there in part because we get better sensitivity because we have a larger energy gap. To create magnetic fields that are strong enough for NMR, we use superconducting magnets cooled by liquid helium. So we have superconducting coils that create the magnetic field. Okay, and in fact, all spectrometers these days use pulse NMR. We pulse with radio frequency of a mixture of wavelengths. We excite all of the different nuclei in the sample at once, and then we use a computer to resolve the resulting free induction decay, or FID, and all of that stuff really is just practical stuff that relates to high-tech NMR machines. We have to do a process called Fourier transformation to sort the mess out. That's what the computer does. And so we usually call our machines Fourier transform FD NMR. None of this really has any chemistry in it. Fourier transform is just a mathematical operation that allows us to sort out the signal from the absorption of all of the different nuclei at the same time. NMR analysis usually requires samples to be in solution for high-res solution state NMR. So we have to use a solvent. Deuterated solvents are used so that we don't have protons in the sample from the solvent that would interfere with our spectrum. The sample is placed in a magnetic field, and the tube is spun at a high rate. Nowadays, you can just ignore that because that's no longer true. The magnetic field variations through high-tech have been reduced to the point where we no longer need to spin the sample, so that doesn't really matter. And there's the machine. The magnet tube goes in the top. There's deuterated chloroform, and probably the commonest solvent used for NMR spectroscopy. Chloroform where the hydrogen has been replaced by deuterium just to prevent getting a huge signal from the solvent. So everything happens, radio frequency and computer console and Fourier transformation, for those who care, ultimately gives you a spectrum on the spectrometer which can be plotted out. Now, the ability to the recognition that different protons at different magnetic fields resonate at different frequencies allows you to apply NMR to all sorts of interesting situations. And so in magnetic resonance imaging, we are imaging the nuclei of, in fact, protons in your body, and essentially different tissues have different concentrations of protons, different amounts of water. So we can make this spatial by recognizing that if we use field gradients such that the magnetic field on your left-hand side is different from the magnetic field on your right-hand side, then the protons on your left-hand side will resonate at different frequencies from the protons on the right, and we can use high-tech computers to resolve all that such that we can tell whether a proton that is resonating comes from your left-hand side or your right-hand side, your front or your back, your top or your bottom, okay? And so we can get spatial information through high technology, and that allows us to do magnetic resonance imaging, which is nowadays getting to be a very popular alternative to doing X-rays of people. And this is purported to be safe because, although people argue about this, there are not really any known side effects from exposure to radio waves or magnetic fields. All right, so that's a little bit of introduction to the theory there. And so now we can go to proton NMR. And I've left this to last, even though, in fact, in the early days, proton NMR was the technique that was used, and NMR spectrometers were simply too insensitive to pick up that small percentage, that 1.1% of carbon-13 in organic compounds. Nowadays, however, it's easier to understand carbon NMR first, and then to work your way towards proton NMR. So, proton NMR works the same way. Proton nuclei have spin. Put them in a magnetic field, the spin states separate in energy, and we can measure the resonances for different protons. And different protons have different environments. They may be more or less shielded by the electrons around the nucleus in a sample. Here's a sample where there are really 3 types of protons, 3 types of hydrogen atoms in 3 different chemical environments within the molecule. So we can count 1, 2, 3, just like we counted 1, 2, 3 in carbon NMR. But you'll notice here that there's a difference. When we count 1, 2, 3, well, wait a minute, that first line is not just a single line saying there's 1 type of proton there. There's actually 3 lines here. And there's 4 lines there, and there's a shitload of lines over here at 7.2 ppm. What the hell is going on? And so the reason that we've left proton NMR to later on is the recognition that there's actually, it's much more complicated than just counting 1, 2, 3. So, what can we get out of this? The number of signals, that's the 1, 2, 3 bit. Remember, in carbon NMR, the number of signals told us about the environment of the carbon nuclei, whether they were shielded or not, what functional groups were present at or around a particular carbon atom. And in proton NMR, the x-axis is chemical shift again. Notice that the range is smaller. Instead of going from 0 to 200 ppm, here we're going from 0 to about 10 ppm in proton NMR. The amount of shielding or de-shielding is less dramatic at the hydrogen nuclei, but nonetheless, information content is present in these spectra. So the number of signals tells us about the number of unique hydrogen environments within the molecule. The signal location, the shift, tells us what those environments are. If we have electron withdrawing substituents, alkyl halide, for example, we might have protons on the carbon bearing the halogen of an alkyl halide might be at about 3.5 ppm, whereas protons in an alkyl group where there's no electron withdrawing substituent, no halogen, might be here at about 1 ppm. So the chemical shift is telling us about the environment of the protons. The second thing that we can get out of this is integration. And this is as far as we'll go tonight. We'll talk about integration. And that is the fact that unlike carbon NMR, where for a variety of technical reasons, we can't count the number of carbons in an identical environment very well, in proton NMR, if we measure the area under the peaks, then we get the number of protons in that environment. So we get 3, for example, a methyl group, the area under a methyl group, such as in fact what this signal is at 1.2 ppm. The area there will correspond to 3 protons, and the area under this peak at 2.6 ppm corresponds to only 2 protons. So there's 3 protons in that right-hand environment. 3 identical protons must be a methyl group, right? CH3. It's the only way you can have 3 identical protons. Here, there are 2 identical protons at 2.6 ppm. CH2 group, right? We've got a methylene group. And something is making it move away, move down from where we would expect a CH2 in an alkane. So this methyl group looks something like a methyl group in an alkane. It's probably bonded to a carbon. This CH2 group, however, has something next to it. It's got a functional group next to it. We can tell that from the chemical shift. Down here at 7 ppm, just like in carbon NMR, sp3 hybridized carbons were on the right, 0 to 100 ppm. sp2 hybridized carbons were on the left, 100 to 200. Right? In fact, the same thing in proton NMR. sp3 down to about 5 ppm, sp2 from 5 to 10 ppm. So hydrogens attached to, so we can tell from the chemical shift that this signal at about 7.2 ppm has hydrogen atoms attached to an sp2 hybridized carbon. We could measure the area under that peak, okay? And you would find that, in fact, that was 5 hydrogens. 5 hydrogens all attached to sp2 hybridized carbons. Here's a big hint, right? You're going to get that from a benzene ring. 6 carbons in a benzene ring, 5 hydrogens, and something is connected to it. What's connected to it? Well, we've got a CH2 and a CH3. So this might be ethyl benzene, right? Benzene ring with a CH2 and a CH3, connecting the bits together, the C6H5 phenyl bit, CH2 in the middle, CH3 at the end, ethyl benzene. It might be something else, too. We haven't quite finished the structure yet, because there might be something like a carbonyl group in between the benzene ring and the ethyl. But broadly, you see, we're getting structural information from looking at the chemical shift of the hydrogen nuclei and from looking at the area under them. On Thursday, we will see why these peaks, there's 3 equivalent hydrogens here at 1.2 ppm. Why is that peak split into 3? And that's a result of the so-called splitting pattern. It's a result of coupling between those protons and hydrogens on a carbon next door. So we'll see how a single line means that we have protons on a carbon with no neighboring hydrogens. Double line, 1 neighboring hydrogen. 3 lines, as shown here. This CH3 group has got 2 neighbors. Okay? And there they are. There's the CH2. It's 4 lines. It's got 3 neighbors. So the splitting pattern is one of the most useful things we can get, because all of the other information, the carbon chemical shifts, tell us about what carbons we've got in the molecule. Proton chemical shifts tell us about what protons we've got. Tells us whether we've got methyl groups or methylenes. Okay? Signal area tells us how many hydrogens in that group. But the splitting pattern tells us how to connect the pieces together. It's like a jigsaw, right? To solve a jigsaw, we have to connect two corners, and we have to go right the way along the side, right? We have to connect all the bits together to get the final solution. And to do that, we need connectivity. We look at, we connect the right little, bubble on the jigsaw into the right hole, right? What do you call them? I don't know, whatever. Okay. So we have to make all the right connections to get the right solution. And so this splitting pattern, as we'll see next week, tells us how to make those connections. So protons with different electronic environments give different signals, right? They have different chemical shifts depending on whether the protons are in different environments. So there's a little bit of sort of fairly complicated stuff here about homotopic and heterotopic protons. We'll run through this fairly quickly because the terminology here is not so important. But here is an alkene, 2-methyl-propene. Okay, and I hope you can see that the two hydrogens in red are chemically equivalent to one another. If I take the molecule, turn it over, I still get the same molecule, but the bottom hydrogen becomes the top one as the top one becomes the bottom one. They have chemically equivalent environments. Those two hydrogens are not distinguishable by NMR. They will give you one signal, okay, and that's all you'd see. The integration would be two. It would be two protons in one environment. CH2F, 2, again, okay, these two are related by a rotational axis of symmetry. For those of you who care and you want to make it more complicated than it is, I think it's fairly clear that those two hydrogens really look the same, and if I take the molecule and turn it over, I can swap them around, and the same with the cyclopropane molecule, the 3-methyl green. So those are hydrogens that are equivalent to one another. They're called homotopic, and they have the same chemical shift. Both hydrogens in each of those pairs would give you a single signal in the NMR with two hydrogens in the integration. You can test this another way. You can do the so-called replacement test. This says that if you take one hydrogen and replace it with something, you take the other hydrogen and replace it with something, if you get the same molecule, the two protons are homotopic. Right? So here we've done that for this first case. Replace the top one by a deuterium, the heavy isotope of hydrogen, replace the bottom one. These are the same compound because I can take that molecule and flip it over, superimpose the first structure on the second, and therefore these two hydrogens are homotopic. Protons that are enantiotopic, we will deal with a little bit more at a later point. Okay? So we haven't talked about stereochemistry yet. We haven't talked about enantiomers yet. That's coming up in chapter 5, I believe. Get excited over that. And we'll see that these two hydrogens here are not superimposable upon one another, but there is a mirror plane symmetry. There's a plane of a mirror runs through the middle of this molecule, in and out of the board, that reflects the one hydrogen into the other. Those hydrogens are not homotopic, but they are related by mirror symmetry. And in that case, we call them enantiotopic. I put this slide in here because when you do, after we have dealt with enantiomers and stereochemistry, it will mean a little more. So enantiotopic protons have the same chemical shift as well. Both of these molecules, the two red hydrogens, would give rise to one signal in the NMR under most circumstances. And in fact, it turns out that the replacement test gets you a pair of enantiomers, which will only make sense when we've looked at chapter 5. And then there are protons that are not chemically equivalent. Here's a case in point. These two hydrogens, we do the replacement test, and we make two molecules which you cannot superimpose upon one on another. This goes back to drawing the wedgies and the dashies, right? And so here, it's important to recognize that as I put a D in the wedgie position, a D in the dashie position, in this particular case, those two hydrogens, those two molecules cannot be superimposed. in this particular case, those two hydrogens, even though they're on the same carbon, would have different chemical shifts. And so we would see, in that case, two signals. Don't worry about this too much. We're not at really the stage of giving you molecules yet where we have these so-called diastereotopic protons. So there are some shortcuts. These two protons are chemically equivalent, and those two are not. Okay, and you can do that, and so on, right? So the two protons in the CH2 group sometimes are equivalent and sometimes are not. That's where we're really at with that. Three protons on a methyl group are always chemically equivalent to one another. Rotation around the carbon-carbon bond in a compound bearing a methyl group, I can move one hydrogen into position where the other one was. And I can always do that. So the three hydrogens in the methyl group are always equivalent. Sometimes, however, things get complicated, as with this example here. Those four hydrogens in this molecule with symmetry, those four protons are what we call chemically equivalent. They will all resonate at the same frequencies through symmetry. And we saw how symmetry also applies in carbon NMR. One of the reasons that I like natural products, and I'm a natural products chemist, is that almost all naturally occurring organic molecules have no symmetry. So we get around all this hideous symmetry problem. So don't worry about this too much. Yes, there was a question here. Yes, and we will get to all that in Chapter 5. So when you come back and revise for the final exam, this may make more sense. Don't worry about it now. The key point is to recognize that protons that are in the same environment will resonate at the same frequency, giving you one signal. Protons that are in different environments will resonate at different frequencies. And sometimes we have cases where two protons look to be equivalent but are not. Okay, so that's an exercise for you to do. And this one again, cyclohexane, we haven't got there yet. That's in Chapter 4. We have axial and equatorial hydrogens, and these are not in equivalent environments. And once again, that will make more sense once you start to draw cyclohexane chairs in Chapter 4. So we won't worry about that. Okay, so tetramethylsilane is our standard, is used as standard for chemical shift. We saw that in carbon NMR. And here in proton NMR, tetramethylsilane has 4 equivalent methyl groups. Each of those 12 protons are all homotopic. Right? The 3 protons in one methyl group are equivalent to each other, and the 4 methyl groups are all equivalent to each other. So tetramethylsilane has hydrogen atoms that are only in one environment, in the same way that it has only one type of carbon atom, and so this turns out to be a standard, a handy standard for proton NMR. So the reason for this is that the methyl groups of TMS come at 0 ppm, which is a region of the spectrum that is sort of far to the right in the normal NMR spectrum. Okay? So by picking a standard that's far out in right field, as it were, we generally don't have interference between the standard and the signals of the compound. So, so there's a formula that allows you to work out chemical shift. Okay, and so this just relates chemical shift to frequency. Frequency is measured in hertz, which should have a capital H there, because Hertz was a guy. So, Klein's mistake. So, essentially, TMS is our standard, and it resonates at one end of the spectrum. We measure a chemical shift away from TMS, right? 2 ppms from TMS, there's a signal. And so, in fact, the chemical shift is defined as the observed shift from TMS in Hertz. That's just really to emphasize that the x-axis in a proton NMR spectrum is frequency, which is energy. Okay, so it is energy. And so to make a unitless number here, to measure the x-axis, we take the difference in frequency of our signal from TMS, and we divide by the operating frequency of the instrument in Hertz. And so that comes out in parts per million. For benzene on a 300 megahertz instrument, so when we use 300 megahertz radio frequency to excite the transitions of the spin, the difference between the protons of TMS and the protons of benzene is really very small. It's only 2,000 hertz in 300 megahertz. These are very tiny effects, but we can measure them quite accurately. And if you plot that, pop that number into the equation here, we get a number that comes out that is unitless, but is measured in parts per million. So here is the chemical shift of benzene, 7.27, and in fact, that is caused by the structure of benzene. It's caused by the resonance of the electrons circulating around the ring that we saw earlier on. Those electrons influence the shift of the hydrogens on the carbons that are attached, make them move to 7 ppm. And likewise, other chemical effects influence proton chemical shifts. Okay. And this just points out that as you change the instrument, if you go to a 60 megahertz instrument, that when you do this calculation, the chemical shift for benzene comes out independent of the instrument. So we just do this calculation so that the chemical shift of benzene is a constant number no matter what lab you're in the world, what size spectrometer you have, bigger, smaller, better, worse. Chemical shift of benzene doesn't change when we measure it in ppm. Most proton signals appear between 0 and 10 ppm. I think I said all. Right, let's keep moving on. This is physics. And let's not even worry about downfield and upfield. Okay, so downfield to the left are protons that are deshielded. They have lower than normal electron density, and upfield is shielded protons with higher than expected electron density. So shielded protons require a stronger external magnetic field to be excited at the same energy as deshielded protons. Why? Well, it's because they're the same as the carbon nuclei that we saw last week, right? So all those nuclei, protons and carbons, are affected by the extent of electron density surrounding the nucleus. So shielded, the energy gaps, and there we go. So here are some representative chemical shifts, and there will be a chart of proton chemical shifts in the test next week and in the final exam, of course. And this gives you a rough idea of where you might expect protons. So here is methane, prototypical alkane, 1 ppm, little bit downfield of TMS, but not much. As I attach a halogen to the carbon atom, the chemical shift of the carbon increases. And notice that the chemical shift of the hydrogen increases as well. Why is that? The carbon-bromine bond, the carbon-halogen bond, has delta plus on carbon, delta minus on halogen. Right? It has a dipole. And that dipole extends a little bit into the CH bond. So when I pull electrons away from carbon in an alkyl halide, the carbon responds by pulling a bit of electron density through the CH sigma bond away from hydrogen. So the hydrogens become deshielded and they move to larger and larger ppm. Notice that as the number of halogens increases, here's chloromethane, 3.1, 2 halogens, the effect increases. Dichloromethane, 5.5 ppm. Common lab solvent, right? So we know where to look. The chemical shift is fixed for dichloromethane. If I see a sharp signal at 5.5 ppm in the proton NMR, then I might consider that I might have dichloromethane solvent in my sample. Chloroform, 7.3 ppm. And notice that this effect falls off quite dramatically as we move away down an alkyl chain. This is important. So it's really only the protons attached to the alpha carbon, the carbon bearing the chlorine, the CH2 group attached to the chlorine, that are dramatically affected by chlorine. They are at 3.3 ppm. quite similar to chloromethane at 3.1. In other words, chlorine, doesn't matter what molecule you're in, chlorine has much the same effect in any alkyl halide. It will shift the protons at the adjacent position to around about 3 to 3.5 ppm. So we can construct a chart, much like we constructed the chart of carbon chemical shift, we can construct a corresponding chart of proton chemical shifts. The beta hydrogens are at 1.6 ppm. They have not moved much, right? Notice that CH2 group that is not directly bonded to chlorine. The chlorine has a little bit of pull of electron density away from the beta position, but not much. And so those CH2 groups that aren't directly attached to the carbon-bearing chlorine have a chemical shift that looks rather like an alkane. The methyl group in chloropropane, 0.9 ppm, exactly where you would expect it to be in an alkane. This is very useful because it means that if I see two protons that are shifted to 3 ppm, okay, then they must be on a carbon that has, for example, a halogen or other electronegative atom directly attached to that carbon. The effect falls off dramatically down the chain. Okay, we can predict chemical shift, start with the standard ppm for the type of proton. Here you see again the terms that we've defined in this course already, methyl, methylene, methine. Notice that the chemical shift is a little different. Methyl groups furthest to the right in an NMR spectrum, 0.9, about 1.2, and then about 1.7 perhaps for methine hydrogens in an alkyl chain. And then this table tells us basically how much to add for substituents on an alkyl chain. So if we have a hydroxy group in an alcohol, those two protons will be shifted by another 2.5 parts per million relative to the methylene group in an alkane. So we start with the methylene group, we add 2.5 for next to oxygen, and we predict the chemical shift for a CH2 group, hydrogens on a carbon bearing a hydroxy group, would be about 3.7 ppm. In an ester, okay, the number's a little higher. So you see that the chemical shift is telling us about the environment of the hydrogens. It's telling us what functional groups are attached to the carbon where I'm looking at the hydrogen atoms. The chart goes on. It tells you what to do if you have two protons next to a carbonyl group. Okay, and so now two protons on a carbon next to a carbonyl group come at about 2.2 ppm. It's about the same chemical shift as the methyl groups in acetone, the common organic solvent. And you can get handbooks that tell you all about where to expect chemical shift. So there's an exercise here, predict the chemical shift of the protons, and I will put up these answers sometime soon. When we have a pi-bonded system, we have an effect that's named by physicists. So it sounds awfully complicated because it's named by physicists. It's called diamagnetic anisotropy. Okay, if you can pronounce it, you pass the test, and you don't need to know it for the exam, right? So I'm not going to say spell diamagnetic anisotropy, right, on the test. All right. This is because basically the electrons interact with the magnetic field. So in a pi-bonded system, like a benzene ring, when you put it in a magnetic field, those electrons in the ring, the aromatic electrons that are delocalized through resonance, start to circulate in the ring. It's like a little electric motor. Closed loop of wire, and the electrons begin to travel. You create a current essentially in the wire. That screws up the applied magnetic field, and as a consequence, protons on a benzene ring get extra magnetic field in the same direction as the applied magnetic field. You can see the little loop circulating here. If that sounds complicated, it is. Okay, you can think about this as being like the Earth, right? The Earth's magnetic field points north to south, and there are magnetic field lines that travel around the outside of the Earth. That's what gives us our magnetic field that we experience. So different regions in space have different magnetic strengths, and some regions are more shielded than others. So here is ethylbenzene, the compound that we started with. There's the structure, okay? And you see that these aromatic protons are shifted remarkably down to about 7 ppm. They're in the range where we expect hydrogens attached to sp2 hybridized carbons. Remember, hydrogen attached to sp2, as in those benzene ring hydrogens, more than 5 ppm. Hydrogens attached to sp3, less than 5 ppm. So all of the aromatic protons, all of these different aromatic protons, they're not all chemically equivalent. The two at the top are equivalent, the two at the middle are equivalent, the one at the bottom is different from the top and different from the middle, and so we see a whole slew of signals. But notice that all aromatic protons, all of these aromatic protons are slightly different, and yet they all come at roughly the same chemical shift, okay? And that is where we expect protons in aromatic systems. Some very large aromatic systems with large rings, 14 aniline. Okay, the protons on the outside come at 8 ppm, where you would expect aromatic protons to be. Protons in the inside are actually at -1 ppm. They're shifted to the other side of our standard tetramethylsilane because now they're inside the ring. Now they experience a magnetic field traveling in the other direction. So we can create a chart that tells us where we expect to see a methyl group, methylene group, methine group, allylic hydrogens, alkynyl, aldehyde hydrogens, okay, notice come out at about 10 ppm. Notice there that an aldehyde hydrogen is at 10 ppm, nothing much else there. So let's ask the question, do we have a ketone or an aldehyde? Infrared spectroscopy. Can you distinguish a ketone from an aldehyde by IR? Not in the carbonyl stretch, anyhow, right? Both have a CO double bond stretch. You can certainly check, you can certainly tell that you have a ketone or an aldehyde by IR. Not so easy to tell whether you have one or the other. Carbon-13 NMR. Can we tell the difference between an aldehyde and a ketone by carbon-13 NMR? No, because both carbons are essentially in similar environments, right? If you look at the carbon-13 shift table, you'll see that both aldehydes and ketones are up around about 200 ppm. You can distinguish them from esters, okay? And so here's the third part of the puzzle. If I have all of this data plus the proton NMR, now in the proton NMR, if I see something at about 10 ppm, I've got an aldehyde. If I don't, I know I've got a carbonyl group. It's not an aldehyde. Therefore, I have a ketone. Okay? It's all about putting all the bits together, the carbon data, the proton data, so on and so forth. Okay? All right. So basically, really what you need to do is go away and practice using the chemical shift table to start to determine structures. Don't go too far, though, because coupling is coming next. Integration is relatively simple. Here is a compound with 4 different types of hydrogens plus couplings. Okay, and we'll worry about the couplings on Thursday. 4 different types of hydrogens. One environment up here at about 0.9 ppm. Look it up on the table. That's an alkyl group with nothing attached. That's electronegative. 1.6 ppm. Something is shifting those protons to and 2.4, right? So there's different protons in different environments. The chemical shift tells me about the environment. But it doesn't tell me how many protons there are in each of those environments. Here, we can measure the area under the peak. And these are typical traces that you see. This is integration in the mathematical sense, right? All of, I don't know, whatever. You know, there's no integration at high school, right? Integration is the opposite of differentiation, yes. Differentiation is mathematical stuff where you look at the gradient of things, right? Okay, so integration is the opposite of that, and you probably do it in math, some god-awful math course here at McMaster, right? Okay, so Integration is measuring the area under the peaks, and these red traces sort of essentially plot out the area under the peaks. So if I measure that area, and in fact in tests we'll give you numbers, we won't give you red traces. Used to do little red traces and make people measure the distance from the bottom of the trace to the top of the trace. Didn't work very well, right? Operating with rulers, not a learned skill in this course. So we proved that. So now we put the number on there so that you don't have to measure it with a ruler. Registrar's office is happy because we used to say, well, you could come with your molecular model kits and your rulers and all this stuff. And then we found people sort of cheating and putting little notes on the back of the rulers. So the registrar's office wasn't too happy with that, so we had to get rid of the rulers, which means we tell you the number here. So here are the numbers. The first one has less area than the second peak. And so the computer measures basically the area under the peak. It doesn't actually tell you the number of protons, but it does tell you relative area. So here's the relative area ratio, 1 to 1.48 to 1.05 to 1.56. So does that mean I have 1.56 hydrogens in one environment? That doesn't make any sense, right? So basically, these are the experimental numbers. And so what we would say is that this rounds up then to 2 to 3 to 2 to 3, right? You see the traces are telling you that there's less area under here, more area there, less there, and more there, right? So what can we get from this? If we have 3 protons in one environment, what do we have? A methyl group, right? So there's a methyl group. 2 protons in one environment. There's a methylene. Another 3 protons in one environment. There's another methyl. And there's another methylene. So whatever structure this compound has, and we may not be able to solve it yet, we can say that there are 2 different methyl groups and 2 different methylene groups, right? So we are building information here that is going to help us solve the structure. How else can we interpret this information? Let's add all the hydrogens together. How many hydrogens are there in the molecule? 10, right? Yes? So we've got 10 hydrogens in this molecule, and no more, otherwise we would see other signals from other hydrogens. Suppose we have the carbon NMR. We've counted the number of carbons from the carbon NMR, right? So we've now got the number of carbons, the number of hydrogens. Suppose we've done the mass spec. We know the molecular weight. And all of a sudden we can get a molecular formula, right? Because now we know the number of carbons, the number of hydrogens, the total of all those carbon and hydrogen units of weight, and the actual molecular weight. So if this molecule had 4 carbons, 10 hydrogens, right? Then that would be C4H10, that would be 58 units of molecular weight, right? Suppose that the actual molecular weight was 74. We're missing 16 mass units. What does that say? How do we get 16 mass units? Oxygen, right? So, proton NMR helps us, at least at the beginning, in the first phase of the proton NMR, we are learning how to get to a molecular formula. Mass spec doesn't give you a molecular formula, it gives you a molecular weight, right? It's not the same thing. So we need to work from the mass spec, the carbon, and the proton to work our way towards a molecular formula. And certainly practicing can do that. So there's a couple of little exercises there, which leaves us then at the really exciting and mind-boggling question of coupling. And so this is altogether a much more challenging thing to understand, because now coupling is telling us about the number of neighbors in a group. But it's critical to solving structures, because we need to we can get the pieces, we can get the methylenes and the methyls, but we need to know what order to join them together in. And we'll pick up there on the message is there quick enough, right? And at this sort of speed, you know, this is a high-speed train, right? On the tracks, and there's a truck somewhere over there, a mile down the track, and you ain't gonna be able to stop.
As a quick question, because we're not seeing a mention from you, are your questions like similar to
Yes,
textbook?
I think we can. No, they're more well, it's sort of a combination, right? There's the multiple choice questions, right? 20 much like Landry's, right?